Welcome, everybody. It's a great pleasure to see so many people in the room. I see the interest. The room cannot keep up with the interest. Welcome also to everybody remote. Small detail for you. You can ask questions via Zoom. We'll pick them later up during the Q&A, so the time allows. And with that, I have just a small organization detail. So for lunch, the lunch break is directly after this call. We have a big lunch area just outside the room and a few more booths outside in front of that area. With that out of the way, it's my great pleasure to introduce today's speakers. Thomas Endres, who is managing partner at TNG. And the one thing that still amazes me is how much time he still has to be involved with all the innovation hacking. We'll hear a bit more what the innovation hacking is in a moment. And our second speaker, Jonas Mayer, who is principal consultant at TNG and unofficially definitely known as Mr. Innovation Hacking. And during every single TNG event, the one thing you always want to do is figure out where he is and what's the latest crazy stuff that he's up to, no matter if it's the innovation hacking with the newest booth or the retro gaming session after dinner in the Retreat Hotel. They will talk to us about how they convinced the robot foundation model that it's actually controlling a roboter that is playing Counter-Strike. And I'm really, really curious to see if the next LAN party I might have with Thomas at a client side, I'd rather play against him or against his robot foundation model and see where my rusty skills are punished harder. And with all of that, I'm really excited to hear your talk, and the stage is yours.
Cool. Perfect.
Thank you.
Yeah, welcome to our session, Skill Issue, teaching robots to play Counter-Strike with imitation learning. In case you weren't aware, we are going to be showing some Counter-Strike footage, so this talk is rated M for mature. In case you have kids with you, this is the time to make a decision. Today we're going to tell you all about robot foundation models and how you can use imitation learning to teach them how to play video games and whether that is a good or a bad idea. Before we do that, we want to again quickly introduce ourselves. I have Thomas with me.
Yeah, we're not going to reintroduce ourselves. Hi, I'm Thomas. I founded the innovation hacking team I think it's already 13 years ago, or something like that. And today with me, Jonas has taken over the innovation hacking at some point in time.
That's right. And so in my position as the head of innovation hacking, I've been working with many different AI technologies over the last eight years. And so we briefly mentioned the innovation hacking, probably a good idea to introduce what the innovation hacking exactly does. We are a team within TNG that creates prototypes that showcase innovative technologies. And we go out into the world and show them to everyone, just like we're doing here today. We brought a couple of showcases with us here today. You can see them in the Verschiebebahnhof, or you can also see a very special showcase over there in the Kesselhaus in the Groot Gaming League area. And one of the showcases that we want to quickly motivate here today, for legal reasons, we have to call it Marlos, but everyone knows it's based on the very famous antagonist from Portal. And we basically built this thing to be hanging around in our office and annoying everyone who leaves their bottles and dirty dishes around. And so we solved this basically with AI. And so from this you can see we are big fans of AI, automation, and obviously also robots. And especially, video games as well.
Especially video games.
Yeah. So video games, that is kind of ingrained into the DNA of the innovation hacking because not a lot of people know this, but Thomas has quite a bit of history in gaming. So this is Thomas 2002.
That's a real image, by the way.
Yeah, this is not AI generated. So Thomas is the guy on the right, by the way. So, and in 2002, he and a couple of buddies started doing LAN parties in his parents' basement. The group grew, and then the thing became regular sessions. They called it the so-called Groot Gaming League. We don't know why they gave it that particular name. And what did they play exactly? Well, obviously Counter-Strike 1.6. You can see here Thomas playing very well, and you can also see that the group really just grew over the years, and they enlisted more and more gamers, and it's kind of insane to think just how lucky Thomas was to have such a big basement. But eventually, times moved on. Thomas moved out of his parents' basement and swapped for a much nicer basement, this one here in the Beterstraße 13. And ever since then, also his daily activities have changed from just playing video games all the time to doing something really exciting, to doing paperwork, reading contracts, participating in public tenders, all of that thing. And so that is basically Thomas's day job, what he spends 20 of his 24 hours in the day with. And that means, well, for gaming, well, that has to become something that he does in the evenings and nights. So here you can see Thomas at a retreat, still like getting in those valuable Counter-Strike 2 hours now, while everyone is having a great time. And this kind of situation here just makes Thomas really sad, because Thomas spends his days doing public tenders, doing fun work stuff, and then he gets home, he's tired, he doesn't want to do anything anymore, but then he still has to play Counter-Strike. So that was about half a year ago, and Thomas thought, what can he do about this? And at the same time, kind of he looked out there and saw, well, now we have robots that have become more affordable and agile than ever, and you start seeing increased potential in automating away everyday tasks. So don't want to go out with your dog, that's okay, just buy yourself a humanoid robot, and then that can take your dog out. Don't want to even own a dog in the first place, automate away the dog as well. So now you have two robots walking each other around, and this obviously is also enabled by big advances in AI that make these robots smarter than ever. We now have these so-called robot foundation models that bring the intelligence and generalizability of LLMs into the robotic space. And so Thomas thinks to himself, well, can't we just use robots to automate away the exhausting part of the day so he can focus on what really matters? And that's how we came up with the idea for today's project. So Thomas decided maybe a robot should just play Counter-Strike for him so he can spend more time on fun work stuff. And that's how this project started, and that's what we're going to talk about today. So, what is it that we're going to talk about today? We're going to give a brief introduction into robot foundation models, where they came from, how they work under the hood. Then we're going to have a look at how you can train your gaming model, how it was done in the past, how we're doing it today. Then we're going to have a couple of a look at different levels of optimizations that we can make to bring our model to the next level, before finally concluding, is this a good idea? Should you do this at home? And what else can we do with this technology? But yeah, first, Thomas, what is a robot foundation model exactly?
Yeah. So let's talk about foundation models first. So we all know about one foundation model, and this is the large language model. So what do we do with that? We just enter a prompt, and basically you get some answer out of that. And this could be anything. So you can pose an arbitrary task to your LLM. So you could, for example, say, what is a foundation model, and get an answer to that. Or you could say that you want a Python function for Fibonacci sequence or something like that. Or you want to summarize an email. So you have a model that can be used for multiple tasks at the same time, and you don't have to swap out models for that. And this is possible with the power of foundation models. So now let's have a look at how could we translate all of that to our robotic world. So in the robotic world, we have something like some cable wiring that needs to be done by a robot, for example, or we need someone who opens the trash can, or someone who wipes the table, or someone who stacks carrots for some reason, or something like that. And at the same time, we don't even have more, we have some tasks, but we also have different so-called embodiments, so different robots that we have there. So for example, we have humanoid robots, we have the quadrupeds, we have grippers, cheap grippers, and all of that nowadays was, or until recently, was done with a single purpose in hand. So we took one robot, we used this one robot, in this case an UR5, to do some table wiping, or we used this specific robot to do some cable routing, or we used this robot again for whatever reason to do some carrot stacking. And the idea behind the robot foundation model now is to not only generalize all the different tasks into one single model, but also for different robots as well. And with that, we have something like LLMs for robotics. And actually what we could do is we could just take a simple LLM. Just ask ChatGPT, hey, I have a picture of my carrot stacking application here, and what do I need to do with that? So here we have a model that understands images and at the same time the prompt, and with that we could then just generate a sequence of actions that need to be done by a robot. This works not out of the box, so if you just ask ChatGPT, then it will just maybe output some instructions, but they might not be the instructions you're looking for. But if you fine-tune a large language model to do exactly that, then we end up with something like the robotics transformer 2. So basically this was fine-tuned to output instructions for this specific robot if we give it a prompt and the images that we get. And with that, we can then ask our model to do something like pick up the strawberry and put it into or put it on the plate or something like that. And now you could say, okay, let's do exactly that. Let's train on all the data that we have out there. So not only one single task, not only pick and place for some banana, which you have to place on 2, 3, or 4, but let's do that for all our tasks. Let's do that for the carrot stacking, for the table wiping, and so on, and so on, and so on. And this is where we end with the OpenX embodiment dataset and the RTX models from the year 2023. And with that, we already achieved something that is pretty remarkable, namely that the generalizing model that was trained on all the tasks outperformed the model that was specifically trained for one task, which is pretty amazing.
Exactly, but that was 2023 though. What happened in the time since? Well, now robot foundation models have really moved forward from these simple beginnings. These days, we have models like NVIDIA Isaac GR00T. That's the one that we're going to be talking about here today. It was released in June of 2025 and has released a couple of model updates ever since. The one that we are using in particular is GR00T N1.5. And this is what GR00T N1.5 does. It's running here in real time, controlling this robot. And it has been trained for tasks just like this, by manual manipulation. So you have two hands, you do something with those hands, you pick up this weird fruit thing and put it on a plate, whatever. Most of the data that it saw is from this GR1 robot. It also saw some OpenXE data sets, so the one that we just saw before. But in any ways, tasks that require two hands, and then we do stuff with it. So let's have a closer look under the hood, how exactly GR00T N1.5 does this. And here we can see it's a bit complicated. We're going to break it down real quick. So we have a multi-part model here. We have a couple of inputs. We have one output. And so let's have a look at the inputs first. So on the first input that we have is a camera image. So that is basically somewhere from the robot system, for example, from the robot gripper. You can have multiple camera images from multiple cameras. You can just feed them in to GR00T. That is input number 1. Input number 2, that is a text prompt. So for example, pick up dice and move them to the plate. So that's basically the prompt that you know from LLMs, because under the hood, that's exactly how that works. Then the third input, that is a very robot-specific input. That is the so-called robot state. And this can be all kinds of sensor readings. This can also be the orientation of the joints. And this is what we're going to feed into the model. Then a lot of magic happens here in the middle, and what we get out in the end is a so-called action chunk. So that's not just one action that it should take, but like a sequence of actions that will be performed over the next, couple of seconds, milliseconds or so. So let's have a look into this robot foundation model, into GR00T, and have a look at the parts that make up this model. So the first stage of GR00T in 1.5 is a vision language model, which is called, what's it called? Eagle. It has 2.1 billion parameters. It is basically a vision language model, so an LLM that can understand images. And you might think to yourself, 2.1 billion parameters, that's not a lot. That's true for LLMs. For a robot model, that is quite huge. And what it does is it takes the image input, the text instruction, and it does some pre-processing, like extracts the information, kind of understands the scene, and passes that on to the second stage, which is the diffusion transformer. You might know diffusion models from image generation, where they generate images by denoising. And the diffusion transformer here does something quite similar. It starts with a very noisy action chunk and denoises it to what we will then output in the end. It gets the input from the vision language model, also the robot state. And then there's these two state encoders and action decoders that we haven't talked about yet. And those are going to be very important for a robot foundation model because those are the abstraction layers for different robot embodiments. If you remember, we have humanoid robots. We also have robotic arms. They all have different kind of kinematic chains. You have to control them in different ways. And so if you want to use one model for all of these different robot embodiments, then you will have to have something like this. The state encoder takes the robot-specific state and translates it into something that the diffusion model can understand, a universal representation. And then the action decoder takes the universal actions that the diffusion transformer produces and turns it into something that we can play on the robot. So this was a lot of maths. Now let's get back to the fun part, because how can we use this for gaming? Well, we already learned, okay, this robot foundation model, GR00T in 1.5, was trained to use two hands. What do we need to game? Well, two hands. So we might be able to use this directly. So let's have a look at back exactly how a gamer works. And so, as you can see in this schematic here, this is rather simplified. We have two inputs. The first one is an image from the screen. The second one we're just going to ignore for now. And both of those are consumed by the gamer and what the gamer produces. Just move a step back so I am on the photo. Thank you. What the gamer produces is some control signals. And you could think to yourself now, well, this kind of looks familiar. What if we just ignore, again, the second input and just place GR00T in here? And so GR00T gets an image and produces control signals for the game. We know the control signals are actually the action chunk. And now we just have to come up with two more inputs. First one is the prompt. Well, here we can just be creative and say, all right, you're playing Counter-Strike. Do whatever. And then we are missing the robot state, and for that, well, we got very creative, and we just said, okay, let's just take the last controller actions that we had, feed them in as kind of the robot state information. And now we have a GR00T that we have kind of adapted to playing video games. So we're done, right? We have a robot foundation model. It can translate to this new task. Let's see how it...
Kind of. So this is our model that we got out. So basically, it really does not know what to do, right? So it just does some random movements. It shoots from time to time and always looks upwards. So this is not what a typical pro gamer would do most of the time. So the problem with that is, at the moment, that we have these state encoders and action decoders, and we did not do anything with them. So we just wired everything up and said, okay, let's do something. Of course, this does not work because we don't have our state encoders trained to the specific way of inputting data or something like that. And that's why we, in this case, cannot just do the same as we would do with an LLM and just put it in and everything will work, but we need to train our gaming model. And somebody else did something like that already. This is from the year 2013 with Google DeepMind, where they learned using a technique that is called reinforcement learning to really play Atari games. So this is pretty cool because somehow it is complicated to play this game, and with some magic, they really learned how to navigate the space and come up with a solution for these simple games. So you could say, okay, that's not a very complex game. What can you do with that? And somehow, OpenAI in the year 2019 came up with something way more complex. So I'm not sure who of you has played Dota 2 before. I have not, and I don't really know what's going on here. It looks very complicated, but somehow this bot was really, really successful, and it bet some world champions. And this was achieved by a bit of resources that we needed. So it was like it just needed 45,000 years of gameplay. It was trained on 128,000 CPUs. CPU cores, sorry, and 256 GPUs. And we said, okay, we won't have the resources for that, actually. And therefore, we thought, hey, can't we do this a bit simpler and just use the robot foundation model. So what we wanted to do is rather have something like that. So the same way we learned Counter-Strike. So we just saw somebody play it and thought, hey, this is cool. And then just looked over the shoulder of this pro PC player or something like that, and then imitated what this player was doing. And with just a couple of hours of gameplay, we could then also start our journey into this world. And this is exactly how we want Groot to learn this as well. So just take some gameplay and use that. And for that, we have to understand how robotic foundation models actually work. And they are also trained using a technique called imitation learning. So basically what we do is we train the model what we want to do. We just do something and the model should then imitate us. So for example, for dice sorting, this is something where we control the arm first. We record the image that we get from the wrist motors, and we also record the robot state. And with that, and with something like 20 to 50 episodes, so 20 to 50 of these just sequences where we do something, we can then train our model. And we do this, we just take the images that we get, we also pick one prompt for our robot foundation model, and then we also have the robot states at this specific point in time. They are synchronized, and then we can just let that run through the system that we have here and get our model output. Of course, at the beginning, this will be pretty much the same as we saw with just Counter-Strike with the raw model. But we can train our model now because we know what the next steps, what the next robot states should be. And with that, we can then just do a comparison between these two model outputs and the ground truth. And actually, we don't even need to train the whole model. We can just freeze the vision language model because we don't want it to learn new things about how to interpret the real world. So that can be just stay exactly the same. The only thing we need to train is the encoder and decoder, and we also might need to train the diffusion transformer. The diffusion transformer might not even be necessary if you have something like pick up dice and move them to the plate. Then the pre-training already had some information about that in it, so we don't need to do this, but for more complex tasks, we could also do the diffusion transformer. And then, when we are finished now, the model will behave like that. So there's nobody controlling the robots anymore, and it will then take the dice and put them on the right plate. And this is pretty cool, and when it's finished, it just stops. And each of the inference steps takes something like 50 to 100 milliseconds to compute, and therefore we get some pretty smooth robot movements out of that. So now we can just train our model, right?
Yeah, so that's how you would normally train your robot foundation model. But remember, we want to play Counter-Strike. So what do we do here? As a first step, we didn't really know if this is even a good idea. We thought, OK, let's do a very low-cost proof of concept without recording our own data. So we went on the internet, we had a look around, and luckily there is exactly one data set out there, the Counter-Strike deathmatch data set. That's 750 gigabytes of 90 hours of human gameplay in Counter-Strike Go. That's more than plenty. Sadly, the wrong version of the game, but OK, who cares? It's the first version. This is what the data looks like. You have, on the one hand, the image that you get on screen, and then what we plotted in here in green is the control instructions from mouse and keyboard. So we have those in the data set as well. We now just add in our constant prompt of I'm just going to step over here for the photo.
No, sorry.
We're just going to add in our constant prompt of, you are playing Counter-Strike. And with this, we were ready to go. We started the machines. We trained our very first version of Groot for Counter-Strike, and we called it XXX Groot XXX V1. So our first attempt at really training a model for bimanual manipulation to play Counter-Strike. And we didn't really expect too much. We just threw it into Counter-Strike and saw what happens, and this is what we got. Here you can see XXX, Groot XXX, playing Counter-Strike, actually doing a decent job, walking down this corridor. It's going to turn to the left here, then decide to go to the right instead. And so it's really traversing this map kind of really well, which is way better than what we saw before. It's going to get briefly stuck behind this container. But if you have a look closely here, then you will see kind of the movement here is really choppy. Like whenever it turns, it does so in very big steps. And also, if you have a look at the crosshairs here, you can see they are breathing. They are becoming smaller and larger. So we're constantly stopping and going. And I mean, in general, this was a very first promising POC. Quite a bit of quite some achievements that we made here. One thing that we noticed, however, from the training data that we gave it, it never really learned to play the game. So once it saw enemies, it never really engaged with them before being killed. And so obviously there's a lot of room for improvement. We also talked about the jerky motion. So let's have a look at how we can level up our model. And we had a look at the data at our model and saw there's two reasons why we have this jerky motion. Number one is simply the way that we run our inference. And we ran it something like this. So all the way in the beginning, you make an observation. That's where you grab the frame. And then you start the inference. So you let Groot process, basically. And once that is done, then we get our action chunk. We can then play that action chunk. So our character in-game will just move. Then once the action chunk is over, we have done all of those actions. Then we stop, do another observation, do the inference. Then we move again. Then we stop, do the observation, do the inference, move on, and so on and on. And who sees a problem with this? Two people. Great. So good that we're explaining this. So in the time when we're doing the inference, obviously our character is not moving. And then also when we are moving, we are not inferencing. And so we can also not react to anything that's going on while we are moving. But this kind of sequence of inferencing, moving, stopping, going is what gives us this very horrible-looking movement. And that's what kind of makes the breathing of the crosshair. And so you could just think to yourself, OK, why do we even stop for inferencing? We could just start with the inference, generate our action chunk, and before we are done replaying the action chunk, we just do the next observation, start the inference, just keep on moving with the new action chunk, and so on, and so on, and so on. And this would be a great solution, right, Thomas?
Yeah, there's one problem to that, and this is this movement that we do here. Well, because whereas we are inferencing, the character is moving, so we start the movement that was calculated from that point in time at some other point in time where we have moved around. So maybe the model would then shoot at enemies that are not there anymore or something like that. And this is something that we do not want to do. So there's a solution to that, and this solution is called real-time action chunking. So there's quite some maths behind it, and it's quite complicated, actually. So we're going to break that down a little bit and just do it with a little metaphor. And so real-time action chunking is kind of like a Jedi that just tells us to use the first few steps in of the movement and just sets them to a specific to some specific values that you have pre-calculated, actually. So the idea is that we now take our robot foundation model, we put in some actions into the diffusion transformer, so the actions that are next to take. And then we use our Jedi to tell our diffusion transformer to output these actions as the first actions in the next chunk. And with that, it will predict these actions. And then when we do inferencing, we can basically, the first step is still the same. Then we do our movement. We can immediately start the next inference step, but we tell it to use these movements from the first one. And then we just cut off the first few movements that we know how they look like. And we start with index 4 and just do these movements for the next one, start our next inference immediately thereafter, and do it again and again and again And with that, we get some smooth movement.
Yeah, that's how we solved the breathing problem, but we have a second problem. We saw when we were turning, like the motion was very jerky, and that comes not from real-time action chunking. That is actually a problem with the input scheme, because it may be a big surprise to all of you in the room here, but it turns out Groot, as a robot foundation model for bimanual manipulation, was never meant to be a PC gamer. I know, it's shocking, no. Groot was meant to be a console gamer. And you could now ask yourself, why is that? Well, if you have a look at how console players play, they use these gamepads, they have these sticks that they use to move around, and you can smoothly move them around, and that's just, yeah, what neural networks prefer. Smooth controls, smooth inputs, so smooth. And so what exactly does that mean? Well, if you have a look in game here, we have those two controller sticks. You move the stick slightly to the left, you move a little bit, you move it a lot. The player in the game also moves a lot around. And then also, with the stick, you have two different dimensions, up and to the side, and those are going to be mapped directly to the two movement directions in game. And then the other cool thing for neural networks is that whatever we get out here is a floating point value between -1 and 1. So a very smooth value that is also, we know it's going to be in the range between -1 and 1, so it is perfectly normalizable. And that is perfect for Groot. Let's contrast that with keyboard inputs. Well, what is this even? We have two movement axes, now we have 4 buttons. They're not smooth, they're binary, so you can either push them or not. And then, like, it doesn't even make sense. We have 4 buttons, what happens if we push A and D at the same time? It's just not defined. And that really scares Groot. Another thing is, well, we also have the mouse input. That is at least kind of continuous, but here we have the issue that, in theory, you could move your mouse infinitely far between 2 frames. I've actually never seen this video to the end. Let's have a look. What happens? OK, server room, very good. Robot, OK. Oh. OK, so we had the issue you can move the mouse infinitely far during 2 frames. That is also just not normalizable, so that really scares Groot. So we thought, OK, controller input, gamepad input it is. The only issue is Counter-Strike has no gamepad support. And why should it? It's a PC-exclusive first-person shooter. It's meant to be played with keyboard and mouse. So there's no native support for that. Luckily, Valve also has a solution for this. It's called Steam Input. And this you can use to basically monkey patch controller input to any game if you want. So thank you, Valve, for the solution for the problem that you just made. Now, OK, very easy. We'll just take a controller, a gamepad Counter-Strike dataset from the internet and train on that, right, Thomas?
There's a problem with that, Jonas, because we now have monkey patched the gamepad into our game, but nobody has ever foreseen that we need a dataset for that, right? So we don't have any dataset that we could use for training. So the only sensible thing that we could do is record the dataset ourselves. And this can then look something like that. So we are at the same time recording the gameplay and taking a video of that. And we can then also record our movements with the gamepad and just put them into a dataset. This is the so-called Le Robot dataset that we are also using for things like dice sorting or something like that. So on the one hand, you have just all the control inputs that you get. So this is basically everything you get from the gamepad. And then you also, for each of the episodes, for each of the plays that you record, you also have a video of the gameplay. And then you also need some glue for that to glue everything together. So this is the data that you need anyways. And with that, we would then have our perfect data set. Unfortunately, nobody has taken the data set or has recorded the data set so far. So we are doing the only sensible thing that every sensible person would do. So we are taking interns for that. So our interns first were afraid when they heard that they would need to record a data set. But then they thought, hey, this is Counter-Strike, right? And look at how much torture we put on them. And They really had a hard time playing hours and hours of Counter-Strike on paid time.
Yeah. And if you want to join these poor souls, here's a QR code. We have a job posting for interns. And yeah, so with this, we recorded our first data set. Before that, we made the strategic decision, who gets to play? Who gets to kind of record the first data set? And we thought to ourselves, if we want high-quality data, we should take the best Counter-Strike player that we have in the office. We have to have an absolute machine of a PC gamer, a seasoned veteran, the best of the best. So we decided to go with an anonymous PC gamer that we cannot disclose for data protection reasons. And we asked him to record a data set for us. And in the beginning, he was very excited to do so. And he came into the office, and then he learned, OK, why does he have to play on this tiny resolution? Then we told him, well, that's just what Groot sees for performance reasons. Then he wondered, where's the keyboard, where's the mouse? And so we basically gave him the controller, and after some very brief acclimatization, he kind of got what he has to do with this kind of input media. And with that, we recorded our very first data set. And the data looks something like this. You can see, well, obviously, it would have helped to have somebody who had played with a controller before. And then also, it turns out, just because you're a PC gamer, you don't know how a deathmatch works. So we got some very interesting data from that. And with this data set, we trained our first proper gaming model. And we called it XXX Groot XXX version 3. And for no particular reason, we decided to codename it Jonas. So here you can see Jonas in action. And right out of the gate, like the movements are way smoother than we saw it in V1. So we don't have the choppy motions anymore. Everything is smooth thanks to real-time action chunking and the controller movements. And let's see what happens when Jonas sees an enemy. Oh, there's an enemy. Oh, and he engages. So that is quite a lot better, quite a bit of an achievement here. We also realized there's quite a few other very interesting behaviors that Jonas had learned from the training data set. So first of all, he had learned to play with different kinds of weapons. Not all weapons are created equal in Counter-Strike. Some of them have scopes. Jonas learned to use the scope. As you can see here, he mostly learned to use the scope, not to aim. But that's something that we can improve on later. Actually, we were quite impressed by just how well he managed to reproduce the aim from the training data set. And then we also saw one of these things. We noticed that Jonas would start shooting in random directions, and we were not quite sure why. And then we found him doing this. And yeah, let's just play this clip for a while. So that is kind of just really impressive that Jonas managed to learn this from the training data set. We don't know why. In any way, we let him play against easy bots in deathmatch mode on Dust 2. And you can see, compared to V1, who just got his ass kicked constantly, Jonas is way better with a KD of 8-20 and a score of 90. But as we saw, maybe there's a better way.
Yeah, and one way to improve that is to play with someone who actually knows what he's doing. And therefore, we took an anonymous console gamer and let him play. And as you can see, the gameplay is a bit better now. And actually, this gamer knows how to aim and also how to play a little bit more tactically. And let's see how this turned out. So this is our XXX Groot XXX version 6. And for no particular reason, again, we called him Tony. And we can see the gameplay here. So here you can see that this one actually plays pretty well. It knows how to aim. It is still very smooth. And let's have a look at a few of the characteristics here. So there are a few things that you can see here. So first of all, we know that in Counter-Strike, at first, the players are protected for a short amount of time, and only after then you can shoot them. And he actually waits for the players to not be protected anymore before shooting them, but gets shot down anyways. And then we also have some tactical gameplay. So you can see him engaging an enemy. Then when he reloads, he actually turns back and goes into cover. And then he engages again. And this is pretty cool. So this is what makes this model special. And Tony actually scored pretty well against the easy bots. So we now have a KD of 26 to 18 with a score of 299. And this is pretty cool, right? So we can actually play against easy bots and win now, which is awesome. Now let's have a look at other maps, because just because it plays well on the data set that it has seen before, how well does it if it plays on data sets that it has not seen before? So for example, up until now we just played with the Dust 2 map.
And Thomas, how long exactly did we let it, like how long was the data set? How much data did we collect?
So we recorded a data set of 1 hour or something like that.
1 hour, that's not a lot. That's not 45,000 hours.
Absolutely,
okay.
Absolutely.
Sorry.
And let's then play with the map Italy. And as you can see, it still works pretty well. It still knows how to shoot the enemies. It also moves around pretty smoothly, even though it has not seen this kind of scenery before. And it even knows how to get around the map. And this is where we thought, okay, it has to somehow learn also to read the minimap, to know where it is located and where it should go. At least that's what we saw. And if we then take Counter-Strike 2 out of the loop and just say, okay, let's use our model, use it for something completely different. Let's use it for Modern Warfare 2 from the year 2009. There's a simple level in that. This is basically a tutorial, the pit. And there we just let it play. And this is what it looks like. So still, it runs around. It does not do it still looks pretty sensible what it's doing. And it's still shooting at the cardboard enemies that don't even look like the Counter-Strike enemies. So this is pretty okay. It's doing pretty okay, even in this game that it has not seen before, based on a training of just 1 hour.
And so maybe it's time to conclude. What have we seen here today? Well, we have trained a very capable Counter-Strike model. And remember that this is not a purpose-built Counter-Strike model. We built it on the backbone of a robot foundation model that has only ever seen biomanual manipulation, except for that 1 hour of gameplay that we gave it. And yeah, that is really remarkable. We saw that it also generalizes to other maps that it has never seen before and does decently even with other video games. So that means Thomas doesn't have to play any other video games anymore, and he can just focus on what really matters. And just look how happy he is. Okay, so this is V6 of XXX Groot XXX, but it's not perfect yet. We still have some limitations in here. And one of the things is what you can see here. So it has a bit of a limited temporal understanding. As soon as a player leaves its line of sight, he will instantly forget about it. And that is simply because Groot N1.5 with the Eagle vision language model only takes one image from the current timestamp. So it has no concept of time. It cannot remember anything. And a possible solution for this is Groot N1.7. This is a newer version that just came out. And what it does differently, it uses NVIDIA Cosmos Reason 2 as a backbone, and that is a dedicated video understanding model. That one you can feed multiple frames. It will get some kind of temporal understanding in here. The only issue for us is that NVIDIA constantly keeps breaking the repository, so we're just waiting for them to get their stuff done so we can start working on here. Another limitation that we have in XXX Groot XXX V6 is it can't hear anything because it only gets an image in, an instruction, and some robot state. And what we are currently working on, what we did some experiments with, is just add in another audio encoder into the equation where we can feed in stereo audio, so from left ear and right ear. And with that, we created our first headphone gamer model, and we called it XXX Groot XXX V9. Here's some early test footage from Groot V9. You can see we are controlling the player here. Groot is controlling the other player. We are just shooting next to him. He cannot see us, but he can hear us and turn towards us. And that is really impressive. We tried it in the lab, And right out of the gate, same training data just from audio understanding. Groot V9 scores way better, like taking the score from 300 to 400. And this is cool. That's also the version that you can test out today. What can we do with this? Well, obviously, in the gaming realm, we saw how we can use imitation learning to very easily, very intuitively give bots behaviors that we want. Before that, you would have to program a bot to behave in a specific way. Now we can just create personalized bots like Tony and Thomas and Toby and Jonas, as we saw before, just by playing a game for half an hour. That is real cool. Another thing that we could do is to actually create a gaming foundation model that has been trained on many different games, and you can basically throw it at any game, even unfinished games, and let it play that. What else could we do is outside of gaming, Thomas?
Yeah, there is, of course, an issue here, because we have now trained a model which was meant for bimanual manipulation to use a video game to shoot at somehow human-like figures. And you could easily translate that into the real world. Of course, we will not do that because we don't do any defense, but this is something where a proof of concept is very, very possible in this case. So there's a dual-use dilemma here, and what looks like fun in games here could easily be translated to something that is not fun anymore. Yeah.
So if you want to do anything like this, don't talk to us. If you want to talk to us, maybe you have another use case that is not military, more in the civilian world, and that uses this very common user interface of the gamepad. Because gamepads don't always have to look like this, Thomas.
Yeah, they could also look something like this. This is also a gamepad, right? Or this. So we cannot talk about this, but we are also working in this area and thinking about what else can we use these robot foundation models for. So if you have a case like that, just approach us.
Yeah.
So now we have come to the end of our talk. So the Groot Gaming League that I founded like 25 years ago was not successful for the last 25 years. But we thought, hey, let's do a reboot of that.
Yeah. And so we brought the Groot Gaming League to the Big Tech Day this year. It is over there in the, what's the name of the building?
Kesselhaus.
Kesselhaus. In the Kesselhaus over there, we brought 3 of our best models. We brought Jonas, we brought Tony, and even Thomas. We don't know who collected the training data for those. But if you want to see how well they play, you can just go there, step on stage, and play against them. But that's all that we have for you here today. Thank you so much for coming here today. And yeah.
Thanks a lot for the great talk. I do have my answer. I'll play against Thomas next time because the models are just going to get better and he's not playing anymore. He will get worse. So that's my best chance. We will spoil a bit into lunch break, but that is long, so I'm not concerned. We have time for questions.
So my question is that probably the other way around, like translating the gamepad to keyboard would work, right? Or the other way around. You have the data for keyboard and mouse,
yeah.
And have you tried to translate it to gamepad and maybe feed it to the network?
That's a very good question, and the answer is yes, we have. That was also one of the first things that we tried. The issue is, even though you in theory get a continuous signal because it's in this -1 to 1 float range, you just get hard jumps, like from -1 to 0 to 1. And that is also really just not very good data to train your model on. And so for that reason, we decided, or we found, that this just doesn't work too well.
Any more questions? I think everybody... Oh.
Hi, thanks for the talk. I'll ask, I guess, a bit more of a technical question. Pi 0 also came out. I guess it works kind of the same way. It's also a diffusion model. Have you tried it? Are there any differences?
The honest answer is no, we haven't tried it yet. We have well, this is quite an early project. Like we've been working on this with a couple of interns for the last 3 months, maybe.
Yeah, something like that. So the idea is we could, of course, use it as well. We have used Pi0 for bimanual manipulation so far, but for this thing, we just we were just stuck with Groot and just tried that out. So this is still a very early prototype, and we, of course, want to continue that work, but at the same time, we have to limit ourselves somehow.
Any more questions? Oh.
Have you tried recording test data with an aimbot or a movement script?
As a gamer, I would have to say no. As a scientist, I will have to say yes. We did that. This was an unsuccessful experiment. I have to say, it wasn't me, it was one of our interns who had downloaded the aimbot and who recorded the data. We didn't really get the results that we're expecting. If you want to know more about that, go talk to the intern. His name is Luca. He's going to be down at the Groot Gaming League all day. He can tell you all about it.
All right. One more. Let's do one more.
Which hardware did you use? Which embodiment? I mean, these arms or what we saw? Or?
The arms that you saw before.
Yeah.
Those are from Lerobo. They are the SO101 3D printed arms, a very low-cost version to get into robotics if you want. And
so these 4 arms together cost like 700 euros, and this is even if you just order the 3D printed part. If you print them yourselves, you get a few $100 off as well.
If you are interested in open source robotics, then what you can do is travel back in time and go to the talk that was earlier today from Lerobo. Or is it coming up? No, it was already here.
Oh,
yeah,
not sure.
Which one?
The Lerobo talk.
Okay.
Yeah.
Just have a look.
Just watch the recording
at the program.
In the worst case, look for YouTube when it appears or the Techday page. Yeah. Thanks again. You will find Thomas and Jonas definitely around. It's probably around the hardware hacking areas and specifically or the gaming area. Enjoy the gaming area. Enjoy the lunch and the rest of the conference.
Thank you.